So good morning everyone. Welcome to lecture 15. And to give you a recap of what we did in the last class, we had introduced this velocity gradient tensor, right? It's an Eulerian quantity. That means it's the gradient, but the Eulerian gradient, grad y of velocity v. And we had also written, we had derived that this is same as f dot f inverse. Okay, and because it's as you will see, it's really a quantity of interest. It has got a name that is L. Okay, and we saw that you can decompose into two parts. It's a general second order tensor, so you can decompose into symmetric and antisymmetric part, that is D and W, and this D is called rate of deformation tensor, whereas this W is called spin tensor. Okay, so we'll see that this is really an important quantity. Both this D and W figure in rate of change of strain measures that we derived in last several lectures. So let's try to work it out and see the rate of change of strains, for example. So let's begin with rate of change of length. Okay, so you can recall that the deformed line element dy is equal to f dx, isn't it? Where dx is the line element in the reference configuration. All right. So we can also write this as ny, that's the unit vector, and then we have the magnitude of dy, right? That's equal to f into nx, right, times magnitude of dx, isn't it? And from here you also see that if you bring this dx on the other side, on the left hand side, then you have dy magnitude dy by magnitude dx, which is same as lambda, right? So we had derived lambda, so lambda times ny is equal to f into nx. So this is something we have derived already, and from here we can also get what is lambda square, that's fnx dot with fnx. So again we have derived this, and this lambda square is the stretch of the line element which was originally in the direction of nx. Okay, so that's how this the meaning of lambda square is. Okay, so let us try to see the its time derivative, because we are wanting to get the rate of change of length, right? So lambda being the stretch, which is the deformed length by original length, so if you take its time derivative, then suddenly this is going to give you rate of change of length, isn't it? So let's find out the time derivative. So that implies 2 lambda into lambda dot, right? That's equal to, now notice here it's going to be f dot into nx dot with f of nx plus f into nx dot with f dot of nx, isn't it? So simple product rule. There are two quantities which are functions of time here, f and nx. You notice nx is not changing with time because nx is the orientation of the line element in the reference configuration, and that is not changing with time. Okay, so having gotten this, you can see that these two are the same thing, isn't it? A dot b is same as b dot a, and then you have a 2 on the left hand side, so that also implies you can write it as lambda lambda dot, that's equal to f dot nx dot with f of nx. Okay, now let's do a trick here. So I'm going to insert f inverse here and also multiply with f, right? You can always do that. And then we have this nx. So this quantity is then dotted with fnx. Okay, so now you can recognize what are these quantities. F dot f inverse is just your L, isn't it? The velocity gradient tensor. And look at this quantity that we have, or this equation that we have derived above. Fnx is lambda times ny. So, and here we have at two locations fnx. So it's lambda times ny. So both of them have lambda each. So we have lambda square then finally. And being a scalar, you can move it to the front. So it's lambda square L ny dot with ny, isn't it? Now notice that this ny is the orientation of the line element in the current configuration, which is a function of time. Okay, but also see that it has become a purely Eulerian quantity now. Let's divide by lambda square on both the sides, and then what we have is lambda dot by lambda, that's equal to L times ny dot with ny, isn't it? And we can further write it as L as d plus w, right? Ny dot with ny, which is equal to d times ny dot with ny. See this, the w, which is the anti-symmetric tensor. So as a side calculation, you should be able to show that for any anti-symmetric tensor w, if you multiply this with a vector and dot with the same vector, then you get 0. Okay, and this is something you can also prove using index notation. So this is always going to hold for w anti-symmetric tensor, and I believe you guys have also done this, seen it in my lecture as well as in the lecture from Professor Arya Samanta, and ny is arbitrary vector for any arbitrary vector. Okay, so please feel free to interrupt me if you have any query. So finally, we have a very important formula derived, that's lambda dot by lambda is equal to d times ny dot with ny. So that's really a important formula. What is the meaning of this formula? What do we have on the left hand side? Anybody, can you tell me what is the meaning of this? Strain rate. Which strain rate? There are so many strains. Rate of unit stretch. Well, unit stretch, what do you mean by unit stretch? Longitudinal. So yeah, it is related to longitudinal strain, of course, because lambda is the stretch, no? But if I want to think of it as a, in terms of words, if I want to write it, can I write it as rate of change of length with respect to WRT, with respect to current length? Can I say that with respect to current length? Because you see, you are also dividing by lambda. So when you divide by lambda, it's like you are making it with respect to current length. Is this something that is that looks okay to you guys? Rate of change of length with respect to current length, not with respect to original length. If it were with respect to original length, well, I should say not with respect to, but per unit. It is per unit. Rate of change of length per unit current length, because we are dividing by lambda. If it were just lambda dot, then it is rate of change of length per unit original length. But it is per unit current length now. Okay. And you see that this quantity is equal to d times ny dot ny. Contrast this with the formula that we had derived earlier, that is lambda square is equal to c times nx dot with nx, where c is the right Cauchy Green tensor, which is either u square, you write it as u square, or f transpose f. But you see, this formula is Lagrangian in nature, it's Lagrangian, whereas this is Eulerian. But the form is similar. The role of C is replaced by D. So when you're talking about strains, actual strains, longitudinal stretch or shear strain or volumetric strain, the quantity to, which is insignificant is C or U square, right? But when you're talking of rate, the quantity that we see here is B. Okay. And you see it's D which is coming up, W is not present here. That kind of also makes sense, no? W is for spin tensor, local rotational rate. So they should not affect strain rates. Whereas D, that's why the name, rate of deformation tensor. So it's D which is responsible for all sorts of deformation, the rate of all deformations. And that's why only D is showing up here. Of course, as of now, we have just done rate of change of length per unit current length. Let's look at other quantities. But before going there, we can also make some physical interpretation of this. For example, this is also written in a slightly different form. That's ln of lambda, and then take its dot. Okay, this dot is the material time derivative. That's equal to again d times ny dot ny. Okay, now what is this ln of lambda? Can you guys recall from earlier class? So ln of lambda is then you can recall it's the Hanke strain, isn't it, or logarithmic strain. Okay, so the other thing to see is D being a second order tensor, it's a matrix, right? So, for example, when you set ny equal to E1, see ny is the deformed orientation, orientation of the line element in the current configuration. So when you set ny equal to E1, so for ny equal to E1, you have lambda dot by lambda equal to D11, isn't it? So D times E1 dot with E1, that's D11. But understand that this does not mean that the original orientation is also along E1. So Nx, for example, is not E1 here. So remember, Nx is not equal to E1, it is Ny, the current orientation, that is E1. Okay, because these are Eulerian quantities, very important for fluid mechanics and also for people in solid mechanics who are doing viscoelasticity, plasticity, where they have to deal with rates, and obviously important for students of continuum mechanics, which all of you are. Okay, similarly, if you choose Ny equal to E2, then what you get is D22. Ny equal to E3, then what you get is D33. So basically what you see is that the diagonal components of D are giving you rate of change of length per unit current length. Okay. Now let's look at the other one, and remember that D in the index form, that's so Dij is half of del Vi over del Yj plus del Vj over del Yi. Okay. Now let's try to look at some other quantities. For example, change in angle. Okay. So can we write that cos theta y, the deformed angle between two deformed line elements, is that going to be ny of 1 dot with ny of 2? Will you guys agree with this? Right? It's very simple from the geometry. Ny is being the deformed orientation, and when you dot it, you get the angle between those deformed lines. So that's why it is theta y. Okay. So let's try to find out what is this going to be. Okay, I think before getting here, because it requires us to also get the, when you find it out, for example, this is going to be minus sine theta y into theta y dot, right? And that's equal to ny1 dot plus ny2, sorry, not this one. So you have to use product rule, dot with ny2 plus ny1 dot with ny2 dot, isn't it? Because ny is the deformed orientation, and that is always going to change with time, right? For a material line element, the deformed orientation changes with time. Okay, so but you see now this means we need to know the rate of change of orientation of the line element also. So let's try to figure that out first before we get to this formula. So to get this, we are going to use the this pink box formula that we have derived above. Okay, so let's do that. So let's rewrite that pink box formula. So we have lambda times ny, that's equal to f and x, isn't it? So let's check the time derivative here. So on the left hand side, we have to use product rule because both the quantities are dependent on time. So we have lambda dot ny plus lambda times ny dot, okay, that's equal to f dot nx. That is it, because nx is not changing with time. Okay, I think all of you are with me so far. Okay, now again, here I'm going to slide inside f inverse and multiply by f and x. So what we have finally is lambda dot ny plus lambda times ny dot, that's equal to big L into f of nx, which is lambda times ny, right? Now let's divide by lambda. So when we divide by lambda, then what we have is lambda dot by lambda times ny plus ny dot. This is what we are looking for, no? Ny dot. That's equal to L and y. So this implies ny dot is equal to L and y minus lambda dot by lambda times ny. And lambda dot by lambda we have derived already, right? Look at this red box, dny dot ny. So we come back here and write it as dny dot with ny and further multiply by ny. Okay, and of course this L and y, you can now write it as dny plus wny, isn't it? So let me write first w part here. So ny dot is equal to wny plus dny minus dny dot with ny multiplied with ny. Okay, simple mathematics going on here. And finally we have what we wanted, that's wny plus, see, I'm going to write it as I minus ny tensor product ny into dny. Okay, can we do that? You see, there's a very nice trick which I have used here, and maybe many of you can recall this. Please feel free to interrupt me, okay? So this quantity, for example, when you work it out, so you see inside you have ny tensor product ny, a second order tensor, multiplied with a vector dny. And how it does? You have to do the dot of the last two. So this is same as ny of ny dot with dny. and this is what you have here, no? Okay, so I have used simple trick here, but then this thing inside the big bracket, can you guys tell me what is this? Some physical meaning of this? I minus ny tensor product ny. So I'm just going to put it in a box here. So think of this very interesting second order tensor, I minus n tensor product n. Okay, and let me multiply this with, let's say, some vector m, where m is perpendicular to n. What do you get if you do that? So if you do that, what you're getting is m minus n into n dot m, but they being perpendicular, this is 0, and you get back your m. Okay, and if you multiply this with n itself, whereas if you multiply this with n itself, then what you get is 0. Okay, so in a way, you see, to this tensor, if you multiply a vector which is perpendicular to m, then you get back the same vector. So for all the vectors which are perpendicular to n, it is acting as an identity tensor. Whereas for vectors which are along n, it is acting as zero tensor. So therefore, it's also called projection tensor. So what you are doing is you are projecting any vector onto the plane whose normal is n. Okay, this is also called projection tensor. And you're projecting it onto the plane with normal n. Okay, and that's a quantity that you have up here also. All right, now let's try to figure out some physical meaning of, so let me first put it in a red box. So we have derived the formula for rate of change of orientation of the line element, or I should say rate of change of deformed orientation of the line element. Okay, now let's choose ny. See, d being a symmetric tensor, no, d is a symmetric tensor, rate of deformation tensor. Why don't I choose ny to be the eigenvector of d? Okay, so let's choose ny because this holds for any ny, any deformed orientation. So let us choose ny to be the eigenvector of d. That means d times, suppose the eigenvector is, what should I say? Maybe nd for the eigenvector of d. Okay, and this is giving you, it will be equal to than the eigenvalue of D, and let's denote that by maybe delta. Okay, delta times ND. Okay, I'm really using some crazy notations here, but just understand that delta is the eigenvalue and ND is the corresponding eigenvector. And remember that there will be three of them perpendicular to each other because D is a symmetric tensor. Okay. So if you choose Ny to be Nd, for example, what will you get? So setting Ny equal to Nd and see what we are getting. So Nd dot, right? So Nd dot is then W times Nd plus identity minus Nd tensor product Nd multiplied with D times Nd. Okay. But notice that D times Nd is a vector along Nd itself because Nd is an eigenvector. So this part, at least, as Manoj is saying, this part becomes zero, isn't it? Because D and D is along ND itself. So when you project it, then it becomes zero. And so what you have is ND dot is then WND. So what this tells you is that the line elements which are oriented along the eigenvectors of D in the current configuration, if you try to find out their rate of change of orientation for those line elements which are oriented along the eigenvectors of D, that is simply W times ND. Okay, which is also, you can write it as ND dot is equal to this W angular velocity cross product ND. You see, this is the angular velocity coming from the spin tensor, and that's why the name is spin tensor. See, this W is the W part which is showing up when you are trying to look at the rate of change of orientation. Okay, of course, for the line elements which are not oriented along the eigenvectors of D, the rate of change of orientation is this general formula. But very special line elements which are currently oriented along the eigenvectors of D, for them you have a special case in which only W is showing up, isn't it? And this formula kind of reminds us that W is acting as a angular velocity, right? That's how the angular velocity shows up, no? And therefore we call this big W as the spin tensor. Okay, this is another motivation for calling big W as a spin tensor. And you had seen the first motivation was when you find out that this big W for rigid body motion, then indeed it was angular velocity. Okay, so I hope you guys are perfectly fine with this. And as I had told you earlier, this big W, you can also write it as curl of V. Sorry, this is small w. I'm sorry. So this is small w is the axial vector of big W, which is also equal to curl of V. It is a half also. This was already done in the last class, no? So this Yeah, so this angular velocity W. Okay, I think I'm messing up with the symbol. So it's the straight W, straight W, straight W. So the spin tensor, big W, you can extract angular velocity from it by just taking the axial vector, or the angular velocity is simply half of curl of V. And the vorticity, vorticity, which is written as this W. You see, this W is kind of scripted W. That is simply twice of this straight W, which is curl of V. Okay, so the vorticity is curl of V, and it is related to the twice of angular velocity. Okay, anyway, so coming back, we have derived this formula for the rate of change of orientation of the line elements. And you see, all these formulas are for the deformed orientation, how the deformed orientation is changing. And obviously, it's the deformed orientation which changes. The undeformed orientation, NX, is obviously not changing, right? So I should say this is same as rate of change of deformed orientation. Okay, now having derived this, we can now go back to our formula where we are trying to find out the rate of change of angle between two deformed line elements. Okay, so let's try to get that. So we saw, I'll just rewrite that formula that we had up there, minus sine theta, theta dot, that's equal to ny1 dot product ny2 plus ny1 dot product ny2 dot, isn't it? So, and let us now write down the formula for ny dot. So this is w times ny1 dot, and then dotted with ny2. Sorry, the whole thing is, so ny1 dot is w times ny1 plus the projection tensor, no, identity minus ny1 tensor product ny1, and this is then multiplied with d times ny1. Okay, I guess I have written things correctly, yes. And then you have to dot this with ny2 plus the other one, which is ny1, and then it is dotted with ny2 dot, which is w times ny2, and plus identity minus ny2 tensor product ny2. Okay, that's quite a big formula, and multiplied with, sorry, not here, it's going to be multiplied with d times ny2, and then the whole thing is within this big bracket, right? So let us see if this can be simplified. Let's, I think one of the things to see from physics would be, because we are looking at change in angle, no? So it is related to deformation. So perhaps W should not show up here, isn't it? W should not show up. So is that something we can see instantly that yeah, W can cut? So maybe let's try to rewrite the W part first. So W part is WNY1 dot with NY2 plus NY1 dot with WNY2. Okay. So yeah, as some of you are already starting to see, it is indeed 0, because this W, see the second term here, if you bring this W on the other side, it's going to be W transpose. But then W transpose is equal to minus of W, right? Because W is an antisymmetric tensor. So when you do that, the first term becomes exactly negative of the second term. And therefore, this actually cancels, right? This is 0. So W indeed drops out. But let us see what we can do with the other things. Can we simplify them? So concentrate on this part. This identity multiplied with this and then dotted with this. And here also you have the same thing. Identity multiplied with this and then dotted with this. Don't you think they are same? So if you write it here, it is dny1 dotted with ny2 plus dny2 dotted with ny1, right? And they are indeed the same, because you, if you bring this d on the other side, then it becomes d transpose, but d being symmetric, d transpose is same as d, and therefore the two quantities, the two terms are the same, so it is 2 times of that. Okay, but then we have some more terms remaining. So that is I think to them we can't do anything. Say what I mean by that. So if you look at this term and this term and this term, what is that? So can you see that this is dny1 dotted with ny1, and then the whole thing has to be further multiplied with ny1 dot with ny2. Does it make sense to all of you? Okay. Likewise, for the other one here, which is this term multiplied with this and further multiplied with this. So that's dny2 dotted with ny2, and then you have again ny1 dot with ny2. Okay, very good. So I think we have gotten some at least contraction of the formula. So so those green terms are going to come here, and finally we have simplification. So it is 2 times d ny1 dotted with ny2, okay, plus, actually it's with a minus sign, minus dny1 dot with ny1 plus dny2 dot with ny2, and you already know what this is, isn't it? and this whole thing is then bracketed with ny1 dot with ny2. Okay, so that's the formula for minus sine theta theta dot. This thing inside the big bracket, each of the terms, they are simply lambda dot by lambda, isn't it? Each of them are lambda dot by lambda, but for line elements oriented along ny1, and the other one is for the line element oriented along ny2, right? This is also lambda dot by lambda. So that's the final formula for rate of change of angle between two line elements. I hope you guys don't have any question till now, but let us look at a special case when ny1 and ny2 are perpendicular. So in the deformed configuration, if we are picking two line elements which are perpendicular in the deformed configuration, that doesn't mean it's perpendicular in the reference configuration. So we are saying pick line elements which are perpendicular in the current configuration. So choose ny1 to be perpendicular to ny2. So in that case, you can see that this is going to become 0, right, for the special case. And then you have a simple formula in that case, that minus of sine theta into theta dot. And what is theta then? Theta is already 90 degree because they are perpendicular, so sine theta is 1, right? So what you have is minus theta dot is equal to 2 times d of ny1 dotted with ny2. Okay, so I'll put both of them in the red box because they are important formulas. And furthermore, if we set ny1 equal to e1 and ny2 is equal to e2, then for those two line elements, the theta dot is equal to 2 times, so with a minus sign, minus 2 times d12, isn't it? You write either d12 or d21, both are same because it's a symmetric tensor. So what you see is that the off diagonal component of this velocity gradient, the symmetric part of velocity gradient, rate of deformation tensor, that is responsible for rate of change of angle. So do you see that this d indeed has a very interesting physical meaning? The diagonal parts, diagonal terms responsible for responsible for rate of change in length, and the off diagonal terms responsible for rate of change in angle. And there is no approximation here, it's an exact formula. Okay, it's an exact formula. So as far as rate of changes are concerned, you can extract it directly from the components of this D matrix. Okay, so I'm going to stop here, okay, and we'll continue in the next class from here. So we have found out today rate of change of length, rate of change of angle, and rate of change of orientation. Okay, the rate of change of angle is directly related to shear strain, isn't it? Because change of angle is shear strain, and its rate is the shear strain rate. Okay, so this is shear strain rate. And this is something people in fluid mechanics often work with. All right, so we have derived an exact formula for the different rate of changes.
So, I've calculated the rate of change in length for the material line element, which
Yeah,
are along the eigenvectors of the D tensor, and also
yeah.
the rate of change in angle for those same material line element which are along the eigenvectors of the D tensor. So, what about the other line element which are not along the eigenvectors of D tensor?
See, this formula is not the line elements along the eigenvector of D. It's for any line element. ny1 and ny2 can be anything. It need not be along the eigenvector. I did say that. Likewise, the above formula, if I go up, this formula in the box, red box here, d times ny dot ny. Again, this holds for any ny. It need not be the eigenvector of D. The eigenvector thing only came up while we were discussing the rate of change of orientation. So because this this was the original formula which holds for any line element, and when we restricted this to the eigenvector, then we got the one in the below. But otherwise, all the formulas that we have worked out, they are for any line element.
So you said for any antisymmetric tensor, W and y dot ny is equal to 0. Could you show that how?
Okay, yeah, sure, I can do that. So I have this W, and say the arbitrary vector is A, okay? W times A dot with A. So can I write this as A dot W transpose A? If you bring this on the other side, can I do that?
Yes, sir.
Okay, but now this W transpose is same as minus of W. So you have minus of A dot with WA, but this is same as minus of WA dot with A, the original thing. Okay, so what you see is that original thing is same as negative of it. So the only way it is possible is that it is zero.
Sir, like you said, the off-diagonal terms are responsible for rate of change in angle. But
Yes,
just to visualize that, you said you assume ny1 is equal to e1 and ny2 is equal to e2. So
yes.
is it valid for that particular case or is it valid for all the cases?
See, the off diagonal terms, when will you get that? For example, D12 is DE1 dot E2. Similarly, D23 is DE2 dot E3, and D31 is DE3 dot E1, right? So, and if you relate the formulas here on the right hand side with the things here, then the two vectors are supposed to be the orientation of the line elements, right? And you can see that The off diagonal components you can get when you have those two line elements perpendicular to each other in the direction of the coordinate system. So by default they are perpendicular. So off diagonal component you can get when you pick perpendicular line elements. Okay. And of course, if the line elements are not perpendicular, then you have this general formula. Yeah.
So this shear strain rate, is it theta dot or minus theta dot?
Okay, very good. It is minus theta dot because you remember from your undergraduate class, the shear strain is the change in angle from 90 degree. So originally the angle would be 90 degree and finally it will become like this. So finally suppose the angle is beta, then shear strain is 90 minus beta. So that's the, and you see here the angle has decreased. Okay, so angle is decreasing. So if the angle is decreasing, we call it positive shear. If the angle increases, we call it negative shear.